discuss in the second or third class of the course. Right? Whenever you have a system, gentlemen, we said that a system is basically a block that has sometimes multiple inputs, one input or more, and may have one or more outputs. Typically, this is a system. Yeah? Now, whenever you talk about system, whenever you want to work about, you work on a system in EE207 or later in other courses, in most situations, you'll have to model that system. What do I mean by model it? Okay, meaning someone could give you that system and tell you, yeah, Abdullah, please, can you go do whatever you want? Tell me, if I put into that system a sine wave, or let's say a sine at the input, what will the output be? Or if I put this shape of signal at the input, I put a signal, let's say, for example, that the system that I have contains only one input and one output. And most of the systems that we'll talk about contain only one input and one output. If I put, for example, in here, cosine 2 pi 5t, can you tell me what the output signal would be? You need to know something about the system itself, okay? But if I'll come to your question, Jihad, if just give me a minute, okay? But basically what I'm saying by modeling the system is you may be given some characteristics of a system. You may even know what's inside that system, okay? And you're given an input and asked to find the output. There are generally 3 ways of finding this output, okay? Or let's say, yeah, there are multiple ways of finding the output, but at least in our course, or let me say this way, there are 3 ways of defining the system there, okay? One of them is you define the system using a differential equation. And we know what differential equations look like. A differential equation, for example, say that if the input here is x of t, and the output, let me call it y of t, then one way of defining that system is to say that y of t will be equal, for example, to the second derivative of x of t, so d square x of t by dt by dt squared plus 3, the first derivative of x of t by dt minus 5 multiplied by x of t will give me the output. Now you'll have to take that thing, plug it in this differential equation wherever you see x, differentiate it and so on, and solve that differential equation to come up with y of t. Sometimes, by the way, this is kind of a simple differential equation. Okay? Why? Because you only have to take the input, plug it in whatever you see there, and add the different components, and you get y of t. So this is quite simple. But other relationships that relate the input to the output using a differential equation sometimes even have the output differentiated. So something like d by dt, which means that to be able to find what y of t is, you have to solve a differential equation using one of the techniques of solving differential equations that exist in the literature. Okay? Now, this is, in most situations, not convenient, although we will do a little bit of this. Okay? But in most situations, this is not the best way that we will do. Okay? Yeah, basically what I'm trying to say here, gentlemen, is to find the output of that system, you represent the system as a differential, or you represent the output as a differential, the output, or let's say you represent the output and the input in a differential equation, and then you try to solve that differential equation to come up with the output. Okay, so this is the first way of finding the outputs of systems. Now, another way of representing that system is using something called the impulse response, which you'll understand, I promise you, inshallah, in the next few weeks. We'll talk about the impulse response, and you'll understand what the impulse response is and how to work with it. Right? The impulse response of a system is usually a function that is given the symbol h in most situations. I'll tell you that the impulse response of a system is h of t. So it's a function of time. And it has some form. For example, this, don't worry about what the meaning of sync in here. Okay? This is not sine, it's sync. Okay? But don't worry about it. Right? Basically, the impulse response will be a function of time. And now, to be able to find what the output y of t is, okay, what the output y of t is, you'll have to do an operation between the input signal and the impulse response of the system. And that operation is called the convolution. Okay? Once you do that convolution, you'll come up with the output. Now, the problem with the convolution operation is that it's a very dull, very nasty, very, let's say, boring and very complicated process. Don't ask me why it's complicated. You see later, inshallah, why using the convolution process is, relatively speaking, difficult. Right? But this is, nevertheless, this is one way for finding the output of a system, is to use the impulse response. Now, another way is not to use the impulse response, but to use something called the transfer function. Now, the transfer function is related to the impulse response of the system. In fact, if you know the impulse response, you can find the transfer function. If you know the transfer function, you can find the impulse response. Right? If you know the transfer function, you can find the output of the system by doing a transformation for two things. You have to take this impulse response, transform it from what we call time domain to frequency domain, from time to frequency. Okay, so you take the impulse response, you transform it from time domain to frequency domain. You transform the input signal, the input, from time also to frequency. Okay, and then work on that system in frequency domain, in what we call frequency domain. Once you come up with an answer, which basically represents the output signal, but in frequency domain, you transform it back. In fact, you have seen this process before, but you don't know that you have seen it. You remember when all of you have taken EE201 or 202, whatever the course number was. And when you reach the topic of sinusoidal circuits at the end of the course, in chapter, I think, 9 or 10, I don't remember the chapter number, okay? But when you reach the sinusoidal circuits, you studied that if you have a circuit, for example, that looks like this, 3 sine 2t, for example, okay? And there's a resistor, a capacitor, and an inductor in your circuit, and you're interested in finding that voltage, VO of t. Okay? You have studied that the process is you take this signal, okay, convert it to frequency. And if you remember, we used to represent it like a magnitude and a phase. Okay? And you take the circuit itself, which is basically nothing but a system, you transform it also to frequency domain. How did you transform it to a frequency domain? The resistor was, for example, if it was equal to 3 ohm, it remains equal to 3 ohm. The capacitor, if it was equal to 2 farads, we converted to frequency domain where its value was equal to 1 over j omega c, if you remember. But I'm not here to teach you the EE202, but I just wanted to refresh your memory. Okay? So we converted the capacitor from 2 farads to its what we call frequency domain representation, or frequency domain value, which was equal to 1 over j omega c. And we converted the inductor into its frequency domain representation, which was equal to j omega l. And then we worked on the circuit just like it's a DC circuit. And we found what is V0. Okay, we didn't call it V0 of t, but we called it V of t. We found what was, I'm sorry, what was, we didn't call it V0 of t, but we called it V0. Time does not appear there. So after we found V0, we converted this V0, for example, which was equal to, for example, 5 with an angle of 20 degrees, we converted it back into a signal that looks like this. Believe it or not, this is exactly the same process that we will do in this course. This is basically using frequency domain analysis. Okay, I'll come to your question, Ahmed. Okay, this is using frequency domain analysis. In fact, we took this signal, converted it into frequency domain. We took the system, the resistor, the capacitance, and the inductance, and converted them into frequency domain. We worked on the system in frequency domain, and once we came up with an answer in frequency domain, we converted it back to time domain to come up with the answer. And basically, those two operations are. Sorry for this figure. I need to correct this figure. I didn't have the application. I copied this from an old lecture note. Okay, so maybe I should have removed it. But anyway, basically what we had is we had an input, we had the impulse response, and we wanted the output. If we use the impulse response directly and use that process that I called convolution, which is a very lengthy process and very complicated process, I would be able to get y of t. But what I'm telling you is that we can do the same process in frequency domain by taking this and converting it into something that we call the transfer function of that system. Yeah? And we take the input, we convert it into its frequency domain representation, take those two, this one and this one, and we can obtain the output here in frequency domain very easily, as you'll see inshallah later. And then once we're done with that, we convert back to time domain. I'm sure that some of you did not understand what I just mentioned. Don't worry about it. I promise you, in the next few weeks, you'll understand this process in detail. Okay? But I just wanted to give you a hint of what we're going to be talking about in the next few weeks. And my apologies, as I mentioned, this figure has some things that should not be there. Those should not be there. And even some of the terminology there is not appropriate. But anyway, but this is basically the process that you see us do a lot in this course. Okay, fine. Okay, a few of you, I think, had questions or comments. If you have any question, please raise your hand or you can just speak. تفضل عبد العزيز. عبد العزيز.
Could you please start recording this session?
Oh, well, my apologies. Okay, I'm really sorry. Well, I forgot. Okay, خلاص, I will start it. Okay, thank you so much for reminding me anyway, but it's, half of the lecture is over. Maybe what I will do is maybe at the end, I will mention everything that I say, okay? Okay, so if you are watching this lecture, after the lecture, or let's say the second half of the lecture, the first half of the lecture, I'm sorry, will come after the second half of the lecture. So if this is the first time that you watch the lecture, please go to the second half about 30 minutes later and watch that part first and then come back. Okay, so my apologies for starting the recording late. Next time, please. Hopefully next time I'm not going to forget, but if I forget, I would maybe ask one of you to open the mic and just let me know that I forgot to start the recording. Okay, so thank you so much, Abdurrahman. Any other comments?
Yes, Doctor.
Okay, Abdurrahman, continue first, and then I'll come to Ahmed. Abdurrahman, you want to say something?
Yeah, our experience with Blackboard is that sometimes it gets buggy, and Microsoft Teams is better. So if you don't mind, I think if we move to Microsoft Teams, I mean, I think it's better, especially when there is too many students.
Let me ask you, Abdurrahman, this is the first time you attend? This is the first lecture you attend?
No.
Okay, because I mentioned the reason why I'm sticking with Blackboard, and honestly, I feel that my hands are tied. Believe me, Wallah, I agree with you. I just had a meeting for 2 hours with a group of 3 or 4 people on Teams, and it was perfect. And I know that Blackboard sometimes causes problems. I'll tell you something. If you face problems, if I find that many of you are facing problems, I promise you I'll switch. And I'm not gonna make you suffer if Blackboard still causes problems, okay? But until I find that many of you are facing problems with Blackboard, let's try to stick with Blackboard. If we have to, I promise you I'll do it. Is this fair?
Yeah, fair enough.
Okay, no. I think you had a comment?
Yes, Doctor. I just wanted to ask about the method that you have just mentioned. You have said that it is easier than the previous method, which is the convolution, as I remember.
Yes.
I mean, for both of them, we'll use a mathematical process, or each one will be in different sharp or different characteristics of solving.
No, both of them are mathematical. Yes, both of those are mathematical. It's just that the convolution process has integration. Okay, integration of the product of 2 functions with several variables, which makes it very confusing and very. I don't want to frighten you from convolution right away, but from my experience, maybe you can turn off your microphone. That's causing Okay. So what happens with the convolution is that it has integration of the product of two signals, the input signal with the impulse response. Okay, and it's not just you multiply the two signals and integrate. If it was like that, it wouldn't be a big deal. But there is a trick in it that makes it a little bit complicated. However, if you go to frequency domain, you're converting that integration of the product into just product of two signals. Okay. Now the trick, let's say, is that going from this. Let me go to TM. What just happened? Okay, going from here, from this to this, okay, requires a little bit of work. It's not trivial, okay, but it's also not very complicated, right? And going back from here back to here also is not trivial, but it's not very complicated, right? And doing this process is quite simple. Is almost very simple, let's say, okay? So the amount of work that you do when you do the process this way, let me just erase everything so that you understand what I'm talking about. Yeah, what I'm saying is to find the output here, gentlemen, we have two ways. Either do it this way or do it this way. Okay? The blue path, although it contains theoretically 3 processes that you have to do, they're much simpler to do than if you want the red path, which only contains 1 process. Okay? This is why it's always preferred in almost every course that uses the concepts of time domain and frequency domain. No one will ever tell you, no, please stick with time domain because it's easier. Because it's almost always. You have seen this in EE202, as I mentioned, or 201. You see it also in many other courses, in communication. You see it in control. You see it in many concepts that in which you can find an output, both in time domain or frequency domain. They'll almost always people will use frequency domain, and this is basically what we're trying to teach you. Basically, what we're trying to teach you in this course is what is the meaning of those blocks. What is the meaning of Fourier transform? What is the meaning of Laplace transform? What is the meaning of different transforms? Okay, which are tools that we will use to take our signals and our systems from time domain to frequency domain. I hope I have answered your question. Okay, but okay. So now what? Okay, now what we will do is we will talk about the topic. I haven't written this topic, but I know roughly speaking what I'm going to be saying. Okay, and that topic is called the transformation of continuous time signals. I mentioned last class that in the first half of the system of the course we will be talking about continuous time systems, and in the second half of the course we will talk about discrete time systems. Since we're going to be talking about continuous time systems, let's talk about continuous time signals and how we can manipulate them, how we can deal with them, and so on. Okay? Now we know what a signal is. Basically, it's a function of time. Think of it this way: a signal is just a function of time. So, for example, if I tell you x of t is equal, for example, to 3 cosine 2 pi 7t, this is a signal. Okay? If I tell you, for example, that y of t is equal to 3t plus e to the power of minus 5t, for example, this is another time. This is another signal. And as I mentioned last time, the most popular independent variable is going to be time. Almost always. I don't remember if we're ever going to be talking about independent variables that are space, for example, or some other independent variables. So since we are almost always limiting our independent variable to time, you see me always represent signals as x of t or y of t or z of t or and so on. Okay. Now, whenever you deal with continuous time signals, which are signals that are defined for all time, sometimes from minus infinity to infinity, or sometimes from minus 5 seconds to 7 seconds, and so on, but nevertheless, they are defined for a range of time, at least, even if we're talking about a signal that is not defined for all time, the signal, for example, will be defined for time for all time between, for example, minus 3 seconds and 5 seconds. Okay, but every point in there, the signal is defined. Okay, it may be there are some situations in which only at one point of those the signal is not defined, but I'll say out of those 8 seconds, the signal is defined for 99.9999999% of the points that exist in there. Okay? So whenever you deal with continuous time signals, you have sometimes to deal with some transformations of those continuous time signals. And the transformations that we're going to be talking about today, and probably next class also, come in two different flavors. One of them is called time transformations, and the other one is called amplitude transformations. Time transformations themselves come in three different types: either time reversal, time scaling, or time shifting. And amplitude transformations also are either amplitude reversal, amplitude scaling, or amplitude shifting. And what we will do today and next class is talk about those 6 different items, let's say. Okay, gentlemen? And to be able to talk about those, I'll certainly give you some examples, and we'll work on some of those examples, but I want you to pay attention. Because if you understand what I'm saying today, it will make your life easier, inshallah, in the near future. Okay. Now, assume that I have a signal. The way I'm planning to explain this is using a model, let's say signal. Okay? A signal that has a specific shape. And we'll see what happens if we apply any of those transformations to the signal. And we'll see what happens if we apply any of those transformations to the same signal. Okay? Let's say that I have x of t. Let me just lay my computer down. Let's say I have x of t that looks like this. Okay? And I'm going to select a signal that is, relatively speaking, simple. Okay? Yet, it has a feature that will allow us to see what is the effect of every one of those transformations. What I'm trying to say, gentlemen, is this. I could have selected, for example, a signal that looks like this. A signal that is always 0 from -infinity to infinity, except, for example, for the time between -1 and 1, where it becomes equal to 1. This is a signal where this is time for us. Okay? The problem with this signal is that there are some transformations that will not appear on this signal. And you'll understand what I'm saying in a few minutes, okay? So I will select a signal that in which the different transformations, all of the transformations will be very visible, so that you understand what are the transformations that we're talking about. And let me sketch it in red. Assume that I have the following signal. Yeah, which looks like a triangle. If you think about it, it's 0 everywhere except between 0, for example, and 2 seconds. This time in seconds. Okay, it increases linearly until it reaches a value, for example, of 4. Okay, at t equal to 2, the value of that signal becomes equal to 4, and then it drops back to 0 and continues at 0. Okay, now this is x of t. If someone asks you, can you tell me what is time reversal? Okay, can you tell me? So now we're talking about time reversal. Let me. Let's say time transformations. Okay, let's say reversal. What do I mean by reversal? Okay, time reversal. What do I mean by time reversal? Very often, you're going to be given a function or signal like x of t, and you're going to be asked to sketch x of minus t. What happens if I remove the t and replace it with minus t? This is basically what we call time reversal. Yes? Now, if this is x of t, can any one of you tell me how x of minus t will look like? Anybody can tell me? Sorry. By the way, if you want to answer, I would always recommend that you click the buzzer, let's say the first. I'm not saying sometimes I pick from the bottom, but very often I'll select the first person. Okay, sorry.
Maybe this triangle will be in the negative side of t.
Oh, I mean like this. By the way, sometimes I like to play tricks on students. Okay, so you may tell me something, and I think that you understand the answer, but I like to maybe tease you. Yes. So, is this what you're saying, Tariq?
Yes, somehow.
Is this what you're saying?
Yes, exactly.
No. Unfortunately, you're not right. What you did is not time reversal. Right. Let me go to. Thank you so much, Tariq. I appreciate your answer. Okay. By the way, if I go to someone else, it doesn't mean that I do not appreciate your answer. Okay. So Abdulaziz.
No, you should be like mirror, the same but
Exactly. Okay. This is the error that you made, Tariq. What you did is you shifted the triangle, and this is why I decided to put a triangle, not like a rectangle. If it was a rectangle, you wouldn't see the mirror image. Basically becomes exactly the same. Yeah. In fact, time reversal means exactly as Aziz mentioned. It's basically a mirror image of that signal around the y-axis. So if this is x of t, x of minus t will look like the following. Think of the y-axis as a mirror. What will you see in the mirror? You see exactly that triangle, but it's flipped. What was to the right will appear to the left. So this is basically how the signal will look like. Okay, Afan? So this is in fact x of minus t. But everything else remains the same. The height, this height, for example, will be equal to 4. This now, instead of being at 2, will become at minus 2. Okay? Okay, so this is straightforward. This is quite simple. Right. What about x? So this is the first, let's say, item. Let me, in fact, sketch them. If you allow me, let me do this. I will do this. I will select everything in here and move it. Yeah. So we're done with time reversal. Yeah. Now, what if we go to the second one, which is scaling? I changed the color. Yeah. What if I come in here and write scaling? Yeah. Now, scaling basically in time, when you're doing scaling in time, what you do is you multiply the t that exists in that signal by a specific factor. Now, that factor could be smaller than 1 or it could be greater than 1. In fact, this is usually how you would write that signal. Let me just write it. Yeah. If someone asks you to write or to sketch x of 2t, anybody knows how it will look like? Now I see Ahmed has his hand raised before I even asked, so I'll go with him. Oh, he decided to withdraw his okay. Ala.
Expand.
Okay. I'm saying expand. Expand by what factor?
By 2. No.
So basically, what
you compress them by half. The half, I think.
Oh, correct. You corrected. Yes. Okay. You see, gentlemen, if I give you x of t like this signal, and ask you to sketch x of 2t, what comes to your mind right away is each t has been replaced by 2t, which means that I will expand the signal by a factor of 2. But that's not right. In fact, usually, when they teach you the time scaling, they'll tell you always write this function that you want to sketch as x of t divided by a specific factor. Now, x of 2t, I can write it as x of t divided by 1/2. And this basically becomes the factor that will tell you whether you have expansion or compression. Since it's 1/2, it's in fact compression by a factor of 2. If I had in here 1/2 of t, yeah, I'll end up with 2 at the bottom in there. So it becomes an expansion. So think of it this way. Whenever you replace t with a specific factor, 2, for example, yeah, since the 2 is greater than 1, then it becomes compression. It's not expansion. Okay? And the compression factor is 2, meaning that anything that was at 5 becomes at 5/2. Anything that was at 10 becomes at 5. Anything that is at -3 becomes at -3/2, and so on. So in fact, if I sketch x of 2t, this is how it will look like. And instead of the 2 that I have in there, I have 1 in here. So this is t, and this is x of 2t, okay? And it will look like this. Everything else will remain the same. So this is still at 4. Okay, gentlemen? This is basically what happens. Remember that if you replace the 2 in here with 0.7, for example, then this becomes expansion by a factor of 1 over 0.7. And maybe I don't know, I selected 0.7. Let's say 0.025. If instead of the 2 in there, I have 0.25, then you know that this is actually expansion, it's not compression. And the expansion factor is the factor of 4, meaning that anything that was at 1 goes to 4. Anything that is at 2 goes to 8, and so on. Okay, Afwan? Now, by the way, you may think that this topic is easy. Just wait until we mix all of those together. Then it becomes a little bit complicated. Okay? So what I'm saying now, I'm almost sure that you probably have seen this before, maybe in some other course in math or so. Okay? But nevertheless, I'm going to explain it to make sure that you understand it. Okay? Before I give you the complete example. So let me take this now and also move it somewhere. As I mentioned, I'm going to write lecture notes that will explain all of this. So you do not have to write any notes after me. Just wait, inshallah, and tomorrow probably you'll get a significant amount, at least 10 pages or so of lecture notes. Right. The last one is shift, time shift. Okay. So by the same concept that we have talked about when we talked about time reversal and time scaling, what if someone asks you to sketch the following: x of t minus 3, for example?
You will go to the right, the left.
But there's minus sign here.
No, if it is.
Yeah, your voice was disconnected, but I think I understood your point. Okay. Yes. Remember this, gentlemen. If you have x of t minus 3, let's say the formula for a shift is always x of t minus t0, where you are shifting to the right by a factor that is equal to t0. So think of this as the formula. The formula says that x of t minus, this is from the formula itself, t0 means a shift to the right by t0, which means that if you want to shift to the left, t0 itself has to be negative, which means that the negative sign will flip this, so you'll get x of t plus 3, for example. So in fact, and what I'm trying to say, gentlemen, is that if you have you want to sketch x of t minus 3, that's a shift to the right. X of t plus 3, that's a shift to the left. Now, some of what I've just mentioned do not make sense, but hopefully, if I have time, I'll prove to you that this is real, maybe in a few minutes. Okay? So if I ask you to sketch x of t minus 3, okay, this is how it will look like. Okay. You take that same signal and sketch it as it is, but we have to shift it. We said, since this is negative, you shift it to the left. I'm sorry, to the right in this situation. You shift it to the right by 3 units. So every point of the signal will appear 3 points to the right of its original location. So the point that was at 0 in here will go to 3. The point that is at 2 will go to 5, and so on. Okay? So this is basically how it will look like. And this point is still equal to 4. Okay? And this is basically how you transform a signal, how you transform a signal in time, either by reversing its time, which what we call time reversal, or scaling its time, which will either give you compression or expansion, or by shifting it in time, meaning moving it to the right or moving it to the left. Now, as I mentioned, those 3 individually are easy to work with. But once you mix them together, it becomes a little bit more complicated. And I promise you that I'll solve a problem for you that will discuss, in fact, all of the 6 different transformations in one example. And if you understand the example that I will solve, hopefully you're not going to have any trouble with this topic at all. Right? So now we have talked about time transformation. Now let's go to amplitude transformation. And in my opinion, amplitude transformation is easier than time transformation for the following reasons. Signal. Let me just copy it and move it. So this is again my same signal in here, and I'm doing amplitude transformation. Okay, and again, just like we had reversal, scaling, as well as shift in time, we also have reversal, scaling, and shift in amplitude. Okay? But as I mentioned, you see that those are easier to understand and easier to use. So yeah? Let's start with reversal. Now, how does the amplitude reversal happen? Clearly, the previous, if you noticed, in all of the previous 3 examples, I didn't affect the x. What I affected is what's between the parentheses. If you noticed in here, for example, I changed the argument of the function x. I removed the t and replaced it with minus t. I removed the t and replaced it with 2t in here. And then in the third case, I removed the t and replaced it with t minus 3. The x itself was not multiplied or added or anything done to it. All of the modifications happened to the argument of x. This is what happens with time transformations. With amplitude transformations, the time remains exactly the same. So all of the transformations will happen to x, to what comes before x. Remember that x is multiplied by 1. If I tell you that I want you to sketch x of t, I can think of this as 1 multiplied by x of t. Now, what will happen in amplitude transformations is this will change. Okay, or what basically the x itself, the function itself, I'll either multiply by something or add something to it. Okay, right. So now, if we come to amplitude transformations reversal, can anyone tell me what is the sketch, or how does the sketch of minus x of t look like? Like I'll pick from the bottom here. Yeah. Oh.
It's mirrored over the x-axis.
Absolutely right. Yes. Like if you remember in the time reversal, I had a mirror on the y-axis, so everything flipped on the y-axis. In the amplitude reversal, you flip around the x-axis now. So basically, your signal will look like this. Exactly the same shape, except now that it will flip. Whatever is above the x-axis will go below, and whatever is below will go above. Okay? By the way, maybe I forgot to mention this. If the signal that I had in here, if this signal had some part that was to the left, when you do time reversal, it will go to the right. And whatever is to the right goes to the left, and whatever is to the left goes to the right. So the same thing here. Anything that is above the x-axis goes below it, and anything that is below the x-axis will go above it. So clearly, the signal now will look like this. Well, this is 2, this is 0, and now this point becomes equal to minus 4. So this is minus x of t. Okay? And this is basically how the signal will look like. Okay, so it's exactly the same as this, except that it's flipped around the the x-axis. Okay, right. Now, as you see, this is quite simple because of the minus sign. Everything got flipped above, with below, and below will go above. Okay? I don't think I need even to move anything in here. Let me go to scaling. What if I ask you, can you sketch for me? What is x of t? But I'm going to multiply this by 2. How does it look like? Jihad?
It will multiply by 2, the amplitude especially.
How come? In the time scaling, when we had 2, we compressed it. Why are we expanding here?
Because we are playing on the amplitude itself, not the time.
You're absolutely right. Okay, this is why I'm telling you that the amplitude, working with the amplitude is easier, because in here it's very clear. If you multiply x by 2, this means that when x was producing to you a value that is equal to 3, now it becomes 6 because of the 2. When it was producing to you a value that is equal to minus 1.5, it becomes minus 3, and so on. Okay, so clearly in here, if you multiply by 2, everything gets expanded by a factor of 2. Thank you very much. Okay, so basically this is how it will look like. So it will look like that, sharper, where this becomes equal to, I think it was 4, now it becomes equal to 8. And everything in time remains exactly the same. Nothing changes in time. Things will only change in the amplitude. Okay? And the last thing is, what if we have the following? What if I ask you to sketch x of t plus, for example, 2, or let's say minus 2, minus 2. minus. طيب محمد الشهري. I cannot hear you, Muhammad. Maybe your mic has a problem.
Yes. Can you hear me?
Oh, okay. Yeah. Now I can hear you. Yes.
We'll take the amplitude and we shift the graph.
Shift it up or down?
Down.
Down. Okay. So this is what Muhammad is saying. Okay. Let's take it back. Okay. Basically, what Muhammad is saying is this: 0 in here, 0 in there. This is 2, and this basically becomes like that, right? Because sorry, I shifted down by 2, and it was reaching a 4, so it will become like this. Is it like that, Muhammad?
Yes, almost. Okay.
No, it's either yes or not.
Wait.
I don't like half answers. Yes.
Wait. The 0 should be shifted, not 0.
Yes. Exactly. Okay, I'm trying to trick you. Okay. You see, what I did is, some people think anything that is above 0 will be shifted down, but the function was 0 from minus infinity to 0, and then 0 also from 2 to infinity. This remains. No, that it doesn't happen this way. Every point of the signal will be shifted down or up based on this. So in fact, this is how you should think of it. Erase it. Okay. This is how you should think about it. Think of it. Okay. The 0 that was here, you see this 0 there, okay, will be shifted down also by 2 units. So it comes here. This function was reaching 4, if you remember, at this point. Okay, so it will be shifted down until it becomes 2. But what happens after that? It was gonna drop to 0 initially. I mean, in the original signal, if you look at this, okay, it was dropping back to 0. Now it will not drop to 0; it will drop to minus 2, and then it will continue at minus 2 until infinity. So this is basically how it will look like. So everything, think of it this way: you take the whole red curve that I've sketched and shift it down. Every part of it will shift down by 2 units. Okay, and this is basically all of the 6 transformations of time domain signals. Okay, any questions on the transformations that I have given you? Any questions, gentlemen? Because now I'm ready to start an example that I'm going to give you on the same signal, but I'll complicate things. Okay, since you don't have any questions, let me erase everything that I have here and give you So let me give you the following example. T is shown. Okay. Maybe I should have written this so that instead of wasting time writing it here, it's shown below. And this is basically the secret. I'll put two parts in it so that one part is similar to the part. Let me even do it in red. There. And in the negative side, this is -4. This is 2. This is 4. Let's see. Okay, this is it. I'm just trying to be accurate. Okay. And let's say this is. I'll just lower it a little bit. Maybe. I had a different function in mind. I just added this now. And let's say this is 2. Okay. So this is slightly more complicated than the previous scene. Okay, that we worked on. Okay. So I think I've given everything. And this is 2. And I want you to sketch the following. You remember the 6 transformations that we have talked about? All of them will be there. Okay. Sketch the signal y of t, which is equal to 2 minus 3. I'm just going to use maybe smaller numbers. 1 minus 2 x of 2 minus 2 minus 3t. Hold on, let me see. Okay, minus t divided by 2, or 0.5 t, right? 0.5 t plus 1. Okay, so this is basically the signal that I'm asking you to sketch. I'm going to show you that it has all of the 6 transformations. Okay, first of all, this minus sign, basically the coefficient of t there is 0.5 with a minus sign, which means that there is time reversal. The 0.5 indicates that there is time scaling. The +1 indicates that there is time shift. So all of the 3 that are related to time exist there. What about amplitude? The minus there indicates that there is amplitude reversal. The 2 indicates that there is amplitude scaling, and the 1 indicates that there is amplitude shift. So all of the 6 exist. Now, some of those are easy to figure out, but some of them are a little bit difficult, especially when they come mixed together. Especially, and I'm talking about the ones that are related to time. Those 3 that are related to time sometimes become a little bit more difficult for you to figure out how you can sketch it. Why? Because they mix together. You see that one of them will affect the other. Yeah, for example, let me ask you this. How much is the time shift? Anybody can tell me how much is the time shift?
1.
So, okay. Like, as it says 1. What about Bara?
2.
Bara? 2. Okay, so I've had 2. Maybe Muhammad Shahri?
2.
Any other answers other than 1 or 2? By the way, when you say 1 or 2, is it to the right or to the to the right or to the left? I forgot to ask.
To the right.
To the left.
You see, yeah. In fact, thank you so much for answering at the same time, because this shows that it's not very clear. Yeah, you cannot just right away look at that and say, this I have, for example, a shift of 2 to the right or 1 to the left, and so on. Okay, you'll have to do it step by step, And this is how I would always recommend that you do it, okay? Start with x of t. Now, once you learn the process, you probably do not have to do it in the same number of steps that I'm going to do. But I will do it for you step by step until we reach the final answer, okay? We're starting with x of t. And let me just copy x of t. In fact, I prefer not to copy and paste, although I can do it, because from my experience, when I copy and paste in OneNote, sometimes OneNote freezes, or basically I cannot do anything. So what I will do is I will sketch the signal again. So let me do this. And I think I only have about 3 minutes. So at least I will be able maybe to start. So let me come in here and put t. Now what I have in here, the signal that I have on top is x of t. Let me do it step by step. Can you tell me what will, let me do it maybe this way. Can you tell me what will x of t plus 1 look like? Anybody can tell me what am I doing here? Hassan Abed.
It's shifted 1 unit to the left.
It's shifted 1 unit to the left, exactly. So I have x of t. All I have to do is just shift this by 1 unit to the left. Okay. So this is basically how it will look like. And please correct me if I'm wrong.
Doctor.
Yes. Okay.
Oh, why did you start with the addition rather than the multiplication?
You do not have to start with any specific one. I'll show you, inshallah, later. If I have time, I'll show you that you can start with the time shift. You can start with the time scaling. Whatever you want, you can start with. Okay? I promise you, I'll show you, inshallah, next class. But I just wanted to show you, I just wanted to start with one of them. Okay? So basically, I have started by putting a shift there that is equal to 1. And so now this becomes equal to 1. This becomes equal to -1. This becomes equal to -5. Come on. In terms of amplitude, I haven't done anything. So again, this is going to be equal to 4, and this is going to be equal to 2. Right? Okay. So now I'm done with one of those, which is basically the 1. Now I want. Okay. Think of this. This is basically what I want you to do. Okay. I want you to think of x of t here as if it is y. So x of t plus 1 as if it is y of t. Think of x of t plus 1 as another signal, or give it a different name and call it y of t. Okay? Okay. The problem is that I only have about few. I'll tell you something. I think I'll stop here because I don't want to rush. Okay, and make a mistake and then regret it at the start of next class. Okay, so I will stop at this point, gentlemen. Inshallah, next class. Most likely, what I will do is I will solve it at home in an organized way, put it in the lecture notes, and maybe I'll discuss it on the lecture notes so that I can speed up. And hopefully, you'll understand exactly what I did, but in an organized way. I'll do it at home, and inshallah, put everything in the lecture notes, inshallah, and discuss it on the lecture notes. Okay, fine. So I'll stop at this point. If you remember, I uploaded the course syllabus on Blackboard yesterday, I think, or yesterday, yes. Okay, and in the syllabus, I think it says that on Thursday there will be a quiz. I'm not going to be able to give you a quiz on Thursday. Okay, so for the time being, assume that the quiz is going to be on Sunday, and probably if I make sure that you'll get a quiz on Sunday, I'll tell you tomorrow what the material of the quiz will be. Okay, fine. So there will be no quiz on Thursday. There is most likely there will be a quiz on Sunday of next week, and I will tell you tomorrow what the material of that quiz will be if I decide for sure that I'll give you a quiz on Sunday. Okay, fine? Okay. Anybody has any comments or questions?
Yes, Doctor.
تفضل.
بالنسبة للهوموركات, are you sure you will be the one who will be grading them, because the university have offered a job for a 207 grader? But they might inform you in the late time after 2 weeks, I think.
Okay, it's good that you informed me. And from my experience in the summer, can you turn off your microphone?
Okay.
Okay. From my experience in the summer, very often they do not find let's say the appropriate graders for some of the courses. Why? Because the people who volunteer, let's say, to do grading in the summer probably is not as many as a regular semester. I'll keep the homeworks there until further notice. Okay, but if I have to grade myself, there's a big chance that I'll just take the marks for the grade for the homework and move it, distribute it on other items. Okay, so for the time being, assume that the homework will still have some marks until further notice. Okay, in EE350, for example, which I almost always teach in the summer, every time I request a grader, almost every time for the past several years in the summer, I request a grader and no grader is fine. But I assume that EE207 will be the same. But I'll leave the mark, as I mentioned, in there for the homework. If it turns out that there's a grader, fine. If there's no grader, then I'll probably cancel, or maybe I'll give you only a few homeworks and reduce the mark for the homework, or do something about it. Okay. So thank you for pointing this out.
اوكي.
Any other comments?
اذا عندك وقت دكتور بس بتناقش معك هذا المثال على السريع قبل بكره عشان انا كنت اليوم. I remember the previous math we have worked with the same concept. بس بدنا نحول الشفت في التايم اكسس بعدين نحول في الواي اكسس ستيب باي ستيب. then it becomes simple. يعني الخطوات اللي سويتها ثلث ساعة نفسها بس بالترتيب خطوة خطوة مع مراعاة ترتيب العمليات اللي هي الضرب بعدين الجمع.
Yes, I understand what you're saying, and what you said is absolutely right. Okay, I promise you, inshallah, next class, I'll show you the different steps where you can either start with the shift followed by the scaling, or you can start with the scaling followed by the shift, and both of them should give you the same answer. It's just that from my experience, sometimes some students mix the two together and they come up with the wrong answer because they didn't know how to proceed. Inshallah, I promise you, tomorrow you'll get a complete answer for this question in a very organized way. Okay, but what you said is absolutely right. Yes. Any other questions or comments?